At the end of August 2024, the world finally met Neo, a groundbreaking new humanoid robot developed by 1X Technologies, who have plans to deliver units to users' homes as soon as next year. We released a 20-minute documentary showcasing the current progress and approach. Following the filming, I had the opportunity to sit down with CEO Bernt. Our conversation dived into his background, his decade-long history building 1X, how they plan to manufacture many robots,
thousands of Neos in 2025, tens of thousands in 2026, hundreds of thousands in 2027, millions in 2028, you can do the math.
and the rationale behind their ambitious goal of home integration. This was a really fun conversation with a lot of offshoots about sci-fi, lessons learned building a company, and how Bernt's cat feels about living with his robots. Bernt, for people who haven't watched the main episode, can you give, who should, before they watch this, can you give a quick breakdown and description of what 1X is doing?
Sure, so 1X is all about solving some of the remaining key challenges in artificial intelligence by deploying humanoid robots into the home and making them truly useful for all kind of tasks, from folding your laundry to building skyscrapers.
So I feel like a big question to ask is, why the humanoid platform? This isn't a new thing for you guys. You've been developing Eve, which doesn't have legs, but has a rolly wheel, and essentially other than that is a humanoid, and you've been working on Neo for years. This isn't just a recent decision you've made. This is something you've done with a lot of conviction. Can you walk through kind of why humanoid?
Sure. So, personally for me, it's a lifelong passion. Knew I was going to do this since I was a kid. But if you think about this, I kind of want to take a step back and say, if you think about generally big breakthroughs in technology. So whether we talk about the transportation sector or we talk about compute is maybe the simplest example of this. All technology kind of goes through these cycles where first you have a very specialized system because the problem is very hard. And for compute, this was the early mainframes, right? And then at some point, you get good enough that you can make a general system, the PC for the computer revolution. And now suddenly you get scale. You get this enormous ecosystem, and you have widespread adoption, and the technology just takes off. And even though, you could say for the PC that for most tasks it was used for, it was overly complicated. You could have done this with a simpler system. There's such a power to having a fully general system that can create an ecosystem. Now, lately, compute has become such a big thing that the market is so big. The market cap for compute is huge. So now you can carve out niches again. They're still large enough that your specialized systems there are still more efficient because you still get scale in your niches.
Like manufacturing or shipping, sort of, for physical robots.
Yeah, right, and ecosystems and software and everything else. Yeah. So this is really what's happening in robotics now. We're going from the era of heavily specialized systems to be able to solve the problem to general systems where you get scale, you get mass adoption, you build ecosystems. And the most general platform I can think of, where I'm very bullish on being the final solution here, is humanoids. Because you want a system that can actually do everything you want to do in the physical space. And then we can start to see all of these benefits that we've seen in the digital space when it comes to creating large amounts of leverage, right? Where there's such an incredible increase in efficiency in society coming from automation of digital systems, but nothing has really happened in the physical space. Now, I do think in the end, we're going to go full circle. We're going to have billions of droids doing all kinds of labor. And at that point, it's going to start to make sense to have a bit more specialization again because your systems are so good. And then we go all Star Wars, right? And you will have different kind of droids for a lot of different things, but humanoids will still be a very large part of it because it will still be the most general system. And then I think, very importantly, all of humanity's knowledge is encoded in our embodiment. So if you ask a large language model how to open a jar of jam, they tell you to hold it with one hand and uncork it with the other. If you think about how we can predict and kind of model how the world evolves, one of the most studied things are humans. If you go to YouTube, there's most video about humans. Now, interestingly enough, humans are pretty freaking complicated. So even with that understanding, models today don't really understand humans that well and how they move, which is a deep subject we can go back to. But I do think there's a lot of value in being able to reuse all of our existing knowledge. And then I think, lastly, not only is the world made for us, but we would really like to make the world even more convenient for us, right? We want to make technology that fits into our world, not make our world so that technology can fit into it. We just want to kind of maximize our own comfort and have more fun, get time to do the stuff that we want to do.
And you think a humanoid platform is the best way to do that as a result of AI, LLMs understanding it through embodiment, and just the world being that desk is about the height of my arm and that sort of idea?
Yeah, and transfer of knowledge, right? I think the last piece here to talk about is the way we teach our systems like Neo how to do all kinds of tasks. And the long tail here is infinite, basically. Is you put on a VR headset, you can see through the robot's eyes, you can see the robot's hands, and it kind of feels like your hands. And the entire body, your entire body is mapped to the robot's body. Now you can do all kinds of tasks that you want to do. And through this create very, very powerful expert demonstrations that our AI can start training based on. And if you don't have a humanoid form factor here that moves as similarly as possible as a human, and we're not just talking about like how it moves with respect to like, oh, it can move from this joint angle to this joint angle. It should have the same dynamics. It should like have the same kind of like impact dynamics. Physics needs to work in the same manner. Then you don't have to think about this. You can just do the task as if you were there. If you think about a robot that's not a humanoid, it's like trolley with an arm on it, 4 wheels, camera in the hand. Maybe it can't actually do this. It can only do this and this. But it can do this 450 degrees. And it's like, go open the door over there. It's actually very hard for you to like figure out, how should I do that in a manner that's like simple and optimal for this robot?
Yeah.
That's called a cross-embodiment problem. And yeah, I think it's an unnecessary complexity. We want to be in our spaces anyway. So, I mean, we could go on and on. There's a lot of good reasons, but I think like, except for kind of like the evolutionary proof that we kind of won evolution in the end because we're so good at using our hands in like a huge envelope and using tools and everything else. Those are the other things that I would highlight.
Well, I find a lot of times too, and I'm curious to hear what you think of that a lot of roboticists or people who build hardware have sort of a negative knee-jerk reaction to humanoids right now because I think they realize how hard it is to do. And they sort of feel like this is just, it's not the most efficient way to engineer the solution, or just because it's never been done, they think it's not worth doing, I suppose, for how hard it is. And I don't know, I still in my mind imagine if you have a humanoid that's working incredibly well, doesn't matter how long it took to get to that point, it's worth it. And those engineering hours are reproduced at scale once you're manufacturing it.
No, 100%. I mean, I think the main argument that I could kind of like, to a certain extent, steelman is, okay, what's the complexity of this system manufacturing-wise? So like, you can always like say you'll make back your engineering hours if this succeeds. But can you make the system so beautifully simple and performant that you can produce this at scale for way less than the specialized systems? And I think we're on a pretty clear path to do that. But it does require you to like take a step back and look at the problem more from a first principles point of view, and not just like keep adding complexity that has typically been the path in robotics. And again, it's about scale, right? So, of course, if we can make a human or robot really, really, really well, we can make a robot arm even cheaper. But we wouldn't make the same amount of robot arms. Yeah. There wouldn't be billions of those. Like, you wouldn't have that as a companion helping you out with everything in life, right? And I do think that's the most powerful driver here is scale. And we see this in all over our society as we look at consumer adoption and in general modern products, that the power of scale is pretty impressive, right? You can squeeze costs down on very, very complicated systems. But I do also think you need to attack it from 2 points. You also need to really think about, how do I make the system as simple as possible?
Before I ask you more about the simplicity, the first principles, and manufacturing of it, as you mentioned, for people who haven't watched the main episode and should watch it, because otherwise this makes no sense, can you explain kind of the heritage of Eve and what Neo is?
Sure. So, 1X started back in 2015. So 9 years down the rabbit hole now. And Eve is basically the culmination of our first generation of technology, where we have developed some very powerful, unique type of motors. So the ones that are in Eve is actually still about 2.5 times more torque to weight than anything you can buy in the market. And like all the manufacturing technology to be able to do this, it's not designed and manufactured in quite the same way as normal motors, the machines to build that. And like putting all that into a platform where we could really roll it out, get good data, get all the lessons learned, figure out how to make this work, figure out how to make the manufacturing work. And that's Eve to me, right? That's the first 6 years of the company. Neo is the second generation of the same technology. And whenever you start out with something completely new, where you've taken a step back and you've done something that hasn't been done before, you haven't really hit the diminishing returns yet on the curve. So there's still like huge improvements between the first, second, third generation, right? So from Eve to Neo, we have an enormous step in both power density, power efficiency, safety, like all of these metrics. And that's what allowed us to go from a wheeled platform to a legged platform that can still go for like hours of missions. It can do all this useful labor. It can be used in kind of any setting. And that can be manufactured at scale and really scaling up all the lessons learned. But if you take that step back and think about like, okay, so our system works by having some very strong motors that allows us to pull tendons, loosely inspired by muscles, so that you can get these beautiful dynamics that you see in nature. Like you see like an athlete running or like doing gymnastics, or like it moves in a completely different way than what you typically think about like stiff, rigid robots, right? We call it a robot dance for a reason.
And can you explain what the difference is between these kind of typical harmonic drives versus these motors that you've developed?
The big crux of robotics has been you don't really know how to make an actuator system, where an actuator system is typically like your motor plus whatever gear you have, plus the power electronics and sensors in the human body. I would say the actuator system is your muscles plus the neural sensor system to drive your muscles and control them. And you haven't been able to make this without having large gear ratios. So whether you're like building a lawnmower or you're building a robot, you have this problem that you have a motor. It can produce a lot of power, so it can spin very fast, but it can't actually produce that much torque or force. To do that, you have to gear it down. And in robots, you typically do like 100-to-1. So you say like, okay, when I move like this, my motor in my joint moves 100 times faster than my arm. And this works really well, right? Because now you have 100 times the force or the torque because you have a gear. So you solve the problem. Now, the challenge here comes from essentially just kinetic energy. So the kinetic energy of any system is 1/2 the mass times velocity squared. And if you do this for a car, we all learn this in school, right? A car that goes twice as fast is 4 times the amount of energy, not twice the energy. 4 times as fast is 16 times the energy, etc. It quickly scales. Scales with the power of a square. So if you apply this now to the rotational part of this, you say, okay, inside here I have a motor that has a certain mass. I have a gear, input to the gear that has a certain mass. They're not negligible. And that is now spinning 100 times faster. Now you have to take that 100 times and you have to square it. So now you have a multiplier of 10,000 on the energy of that system. And the way to think about this intuitively is if you have something pretty heavy that's spinning very, very fast, it's not going to immediately stop. That just doesn't work, right? So if you now have the arm not moving so fast, but inside here, this is moving so fast you can't see it. When your arm hits something, this cannot instantly stop. And you can actually do a very simple mathematical breakdown on this. This is just kinetic energy. You can say like, this system has a certain kinetic energy. What is the equivalent weight that needs to be here? If we remove this system and we say, we want to put some weight here, that means that when this system is moving at this speed, it has the equivalent kinetic energy to what it had. You actually usually for a robot arm come out somewhere between like 30 and 60 pounds. So that's like when you see a robot arm in a factory moving like this, even a small one for just moving like 5 kilograms, something like that, or about 10 pounds, you can picture that someone strapped a 60-pound kettlebell to the wrist of that robot when it's moving around. And now you know why industrial robots are incredibly dangerous. And that's why they're in cages. And this worked so well in the industrial paradigm because this system actually has another very beautiful property. Because these people were really smart. This was designed back in the 60s, most of this. And when you have such a high inertia or mass, it's very hard to disturb. So like if you're moving and I try to stop you, you're not going to stop at all. So this means all the different parts of this system, like multiple joints, etc., they didn't actually disturb each other. So now you could just control one joint at a time, and the system would be very stable and nice. And you didn't have the compute power to control all of them at once. So that was actually a necessary condition for this to work. In the factory, you just calibrate, and now you know exactly when the robot is supposed to touch something. So you slow down, and then you move fast again. And in classical robotics, we call anything where you're touching something that wasn't planned, we call that the robot collided. And usually something breaks.
It's normally not good.
Yeah, it's normally not good, right? Your arm collided. Now, if you think about how you live your life, you collide all the time. It's actually all you do. You just collided with your notes, right? You take one step, that's collision with the ground. And you never know when you're going to collide in general. It's not all planned. And your sensors aren't good enough to know exactly when it happens. So in this unstructured world, where there is like a home or even like in a warehouse, right? You need to just have a system that is able to interact with the world like humans do. We have so little energy in our motion. It's all nature does. Minimize the energy needed to move. And then you get this beautiful interaction dynamics where like if I turn around fast and you were behind me and I accidentally hit you, might be a bit awkward, but you're not going to die. It's kind of counterintuitive, right? How dangerous robots actually are. But it is because we don't really appreciate enough, like how much evolution really went deep on this problem. Like how do you minimize energy? And how important it is, not only for being able to do tasks, but for safety. And the mirror of this is, of course, that we are also pretty safe with respect to ourselves, because we don't hit the world that hard. And this means we can explore. And if you think about these systems learning in the real world, the ability to just try things without breaking the world or breaking yourself, that's a key component of how we learn. Because today's systems generally learn, so artificial intelligence systems, they generally learn through pure observation. We train on all of the observations humanity has done. But how humans learn has a lot to do with experimentation, right? We do an action that changes the state of the world, then we observe. And we're like, oh, this leads to that. And so much of our reasoning comes from this. And this is also something that is really, really important to design into your system so that you're able to actually explore in the real world if you want to learn in the real world.
So how do you do that with the robots you build? How do you design them to experiment and have a sort of a feedback loop and a learning system built in?
Yeah, so first of all, we already talked about, it's all about having a system that has very little energy. So there's very little energy getting exchanged between the world and the robot when they touch each other. This makes it inherently just soft and safe. And this means that you can try to open a door for 8 hours without the door or the robot breaking. So now you can just try until it works, right? You can figure out how to do this. Now, we do help the robot, like I talked about earlier, with saying, like, okay, I'll open it in VR first a few times with the robot so it knows how to do it. But
that's off of vision. It's not necessarily just off of like the robots you build can't sense touch.
Oh, it can.
They can.
It can sense touch, which is one of the reasons it's so important to do it with a robot and not just like have a human walk around with a camera on their head and do the task. Because the robot actually has the ability to sense what is happening. Yeah. And it knows also its own state. It knows a few important things. It's almost like cheating because it knows what action it was trying to take. It knows what state it was in. It knows what forces is acting on it. And there's, of course, opposite, which forces are acting on the world. And these modalities don't exist in today's data sets. Yeah. And we see that they are incredibly powerful modalities to get a better understanding of how the world works. Now, naturally, like it's pretty obvious that this will help you to learn physics because, I mean, you're experimenting with how physics evolves the world when you take actions in it. But it's also really interesting to just think about like how these physical actions can ground all kind of models. So like you go into the bathroom and you ask, is the toilet seat up or down? It's a canonical fun example where
We filmed this example today.
you did. Yeah, that's good. That's really cool because it's an edge case, right?
Yeah.
So in general, that's a modern model like GPT-4 is able to answer that question really well.
Yep.
But this specific one like just always fails. 50-50 if the toilet seat is up or down. And
Interesting.
that's interesting, and you can talk about like why that specific thing is hard, etc. But I think the important part here is that there's an infinite long tail of these kind of edge cases that fail. So how do you start actually grounding your model in reality? So you know if whatever conclusion you came to is actually true. Well, you close the toilet seat, right? If you now it's closed, I know it's closed because I just closed it. Now you actually have a feedback loop on this.
Right.
And that is like one of the things that I think is incredibly interesting when it comes to overcoming some of the current challenges in these kind of models. And then, of course, in the end, as we add all of these modalities into the system, you will just have, in general, a way better understanding of the world, which will allow you to reason better about any kind of task.
What are the main differences, to take a step back, between Eve and Neo? Obviously, the only one I can see is that Neo's got legs, Eve's got a really cool lower body that rolls around and stuff. Talk a little bit about that difference in some of the other ones, and why a whole new robot is needed.
So I think maybe the biggest thing between Eve and Neo, which is hard to see, is how the entire system is designed for passive safety. And what I mean by that is we want the impact energy to be below the threshold for what's said to be likelihood of severe injury if everything goes wrong. So this is like the robot running. You were lying on the ground and the robot accidentally kicked you in the head. Or the robot is like falling and it falls on. We'll do everything we can to make sure this doesn't happen. And like we're sinking so much work into foundation models for robotic safety, all these things. But I do think we have a big responsibility that if you're going to get to billions of robots on the planet, they need to be as safe as possible from the hardware perspective.
Right.
Because things will go wrong.
Right.
And we don't have to make this into a big, industrial, heavy, dangerous machine and kind of like get into the same corner as autonomous cars. We can try to make this as safe as possible. And to do that, first of all, you need to be very lightweight. So Neo is only 66 pounds, but it can lift 150 pounds. So it's about like athletic performance for a human. There's no pinch points. Like wherever you put your fingers, you can't really pinch your fingers. It's extremely low energy in motion, like we already talked about. So if it accidentally hits you or kicks you when running, these kind of things, then the system should still be as safe as possible. And also the entire robot is actually soft. So if you try to compress it like this, it compresses almost like you. And interestingly enough, we can use some of the tendons underneath to like support the structure that is compressing. And this combination really enables you to make a system that is just extremely safe compared to anything else. And I do think safety is one of the biggest barriers of entry into this market if you want to put it among people. If you want to put robots in cages in a factory, sure, it's not a problem. But you're not going to learn much. Yeah. And we're starting to get a lot of data on this now, where we're seeing that after you do a task about 50 times, the performance doesn't really improve. Now, this is at pretty large scales of data, because our robotic foundation models now are starting to get pretty large. So, of course, in the beginning, when you don't have any intuition about how to do any task, you do see improvement. But once you get to a certain scale of data, you can learn a new task with around 50 samples and be quite good at it. Like, you're better at it after 5,000 if you balance your data correctly, but like you really hit diminishing returns.
Yeah.
So what you would really like is to have like 50 samples of picking up every cup in the world in every place in the world with as many different like people, cultures, whatever in the background, voices, chaos, whatever, right, as possible. And that diversity, that's where we get intelligence. And it's the same for people, right? People need to experience a lot of diversity when growing up to be really good at something. You don't get the best in the world at neither progressing science, like if you want to be the world's best physicist, it's very useful to know a lot about other disciplines.
Yeah.
And even if you just like want to be the world's best tennis player, it's actually very useful to have played different sports. And this is not different for robotics. And it actually wasn't different for language models either. I mean, the best models are the ones that have the best diversity in the training data set. And this is very public knowledge now. Even if you like read the newest paper from Meta about Llama 3.1, which is very close to state of the art, they say like the difference between Llama 1, 2, and 3, there's almost no difference in the architecture. They're training slightly longer because compute cost is coming down. But like the absolute main difference is they have a more diverse data set. It's all about creating the most diverse data set. That's where your performance comes from. That's where intelligence comes from. And for some reason, people think that this is not true for embodied agents and robotics. So they think like, oh, you can just start with like a very narrow wedge. Like I'm going to do an industrial use case where I'm going to move this thing every day. That's all I'm going to do. Then I'm going to learn. You're not going to learn very much. You have to actually be out there and see the long tail of all possible things that can happen. And through that diversity, you can create a truly intelligent system. And now you can go and look at all these other problem spaces, and you could solve them with like, I don't know, 50 samples. That's what you do as a human too, right? I show you how to do a task. If it's a pretty menial task, I show you how to do it, and you're like, oh, that's fine, I can do that now. Because of all of your existing knowledge. And I do think the path to truly intelligent androids, so that we can actually have billions of them on the planet doing all kinds of physical labor, is first through the home, so that you have this diversity of data. And then after that, you can go and capture like manufacturing, services, whatever. Doesn't really matter.
What is the name, you would remember, I wouldn't, of that principle where if it's easy for humans, it's hard for robots. If it's easy for robots, it's hard for humans?
Moravec's paradox.
Moravec's paradox.
Yes.
What have you found of this principle to be, how have you found it to be in building a robotics company for 8-9 years now? Is it true? Is it false? Where are the kind of edge cases with it?
So if you think about Moravec's paradox, there is something to it. We've clearly already experienced that like creativity is simpler than we might have thought. Language, etc., etc. Now, when it comes to higher level reasoning, these kind of things, I don't necessarily agree that we've solved that to an extent. So, yeah, I don't quite buy that like that's a proof point. But a lot of these things were easier than we thought it would be. When it comes to the embodied side of it and actually doing the tasks, we also have examples of things that we thought would be extremely hard to do that is actually easy to do, and opposite. So I do think it's an oversimplification, and we see sometimes that things actually work a lot sooner than we thought, and maybe a lot of the problem isn't really Moravec's paradox, it's that we just haven't had good robotics data. No one has had it at scale. But there is some truth to it. There is some truth to it. I think it's very interesting, though, how all of these things belong together. So if you want to be good about reasoning, it's pretty important to be able to be good at manipulating. Even though they don't have anything to do with each other, you would think like, but if you're very good at manipulating, you can actually do a lot of experiments. And if you can experiment and observe, then that's kind of leads to reasoning capability. So a bit of an oversimplification, but there's some truth to this. There is some truth to it. But I do have a very interesting one, which is a different kind of like more, maybe it's more a philosophical experiment, but are you familiar with Mary, the super scientist?
No.
Okay, so probably going to get this wrong, but I'm going to try to explain it simply. So Mary lives in a box, and she can only see the world through black and white monitors. And she is a super scientist. She knows absolutely everything about light and how it correlates to color. So like how it hits, when it hits your retina, like how it goes to your brain, how your brain processes this, like how every neuron fires, why, wavelength, everything there is to know about light, she knows. Now, one day you open the door and you let Mary out. Does she learn anything? It's very easy to draw this parallel to like, you have a box.
Yeah.
The box is observing.
Yeah.
It can never act.
Yeah.
It can never, and like our intuition tells us, right, that like clearly she learns something. She hasn't experienced the world. But it's actually a very hard question. There's like multiple books written about this single experiment.
Would she learn anything? I'm not sure, but I think, I mean, honestly too, you could argue that like black and white 2D images are really simple. And even if you know everything about color, as soon as you start talking about three-dimensional space, how things move through time, and you take that metaphor into the robotics parallel.
But the point is, she has a lot of information. So by first principles, she clearly did not learn anything. Because if she learned something, then we're saying that like our understanding of the world is something of like a higher order nature. It is not purely the information. But my point with the experiment.
Yeah, I see what you're saying. Yeah.
You can make like a God complex thing out of this. But the point is that I can't solve this philosophical question. But what I can tell you is that it's a really freaking hard way to go about the problem. Yeah. I'd much rather be outside the box.
Yeah.
So I think the important takeaway here isn't whether you can have an AI learn purely from like observing passively the world through very limited modalities. It's just incredibly inefficient, right? Like the amount of information you need about color to understand color from text comparatively to just understanding it from a picture or even better a video, right? Well, you kind of can. You see large language models.
That's fair.
Trained on pure text actually have a pretty good understanding of color.
That's a very good point, actually.
Incredibly inefficient way to learn this.
Yeah.
So the engineer in me is like, why would you do this? And the honest answer is generally like, well, we don't have the data, so we have to do it. But we can actually get that data, right? And through that, we can make some hopefully pretty big steps in the direction of a intelligence that can be more useful.
Earlier you mentioned you don't think we've solved higher level reasoning. We don't fully have it figured out. Can you talk a little bit about what you mean there?
I mean, all our current AIs completely fail at most reasoning tasks.
Most what tasks?
Most reasoning tasks.
Recent tasks.
Reasoning.
Ah, yes.
So like if you actually have to reason about a problem to come to a solution, it's very different from just kind of like reiterating the correct summary of all the observations that we have fed it during training. And there are some kind of like signs of life that it's there, kind of, right? It's actually easier to show this in image models where you can get what we call auto-distribution successes. So like DALL-E creating an avocado chair, even though it's clearly no avocado chair in the data set. But also you can say like there's an avocado, there is a chair. You can like, it's a pretty limited reasoning to combine them, but there is a kind of reasoning.
Yeah, there definitely is.
But reasoning capability is typically something you see emerge from having a very good understanding of the world so that you can experiment and observe. This can be done in the digital realm. It doesn't have to be done physically. It's just the physical world is a lot richer. So if you think a lot about like AlphaZero, for example, from DeepMind, right? It's a pretty interesting paper because this combines the ability to explore the world, see the outcome of your actions, and also to search in that space. And doing that in the real world really excites me. And we don't have the answer of where this ends, but it really excites me. Early results are very promising. And I think we can create something that adds a lot of value.
So talk to me more about that. What is sort of the 1X approach to intelligence and AI? Are you training models that are taking in like different sensor data and image data and feedback data? How are you approaching this? And yeah.
The short answer is we're doing all of it. So all these modalities are useful. So like, of course, you train on all text that's available. You train on all images that are available. You train on all video that's available. this gives you a pretty good like foundational understanding of basically to the level of like a modern large VLM, right? Now, in addition, you train on all of your robotics data. And all of these, and you train on some simulated data. And all of this is useful to get you to your end goal, which is to just get an intelligence that can better reason about the real world and have good like spatial understanding. That's a current very big problem. Like if you ask a modern VLM today, just like if I move forward for 1 meter, will I collide? It's very often wrong. It has very bad understanding of like spatial aspects because again, it never did that, right?
What is a VLM for clarity?
So a VLM is a visual language model. So it's basically a language model that is also trained to be able to think about images.
Got it.
Yeah. And often now also video, but we still call it a VLM. Audio starting to creep in there. And you see this clear trend, right? As you're adding more and more modalities, the system gets smarter. Sure. And this is about adding kind of like even more modalities. But in the end, it's about creating a data engine where there's kind of like no limit to what you can learn, right? And I do really believe that the future of science is billions of droids running experiments in labs all over the world. And through that, progressing our understanding of the universe. And it's very hard to do scientific discovery if you're not able to actually carry out experiments.
That is I hear a lot of people talk about what inspires them on deeper and deeper levels is understanding the universe better. And often you hear people who talk about space, and they want to go deeper into space to understand the universe better. And I don't think this is bad. I think we should go into space, but I doubt that is the most efficient way to do it necessarily. And what you've said, I think, makes a lot of sense. To take a step back, though, I'm curious if you could like break down exactly what you mean by training. You're saying we're training synthetic data, we're training this VLM data, we're training our own data, sensor data. How are you training it? How are you kind of fusing it together?
So the simple answer here is to just like refer to the bitter lesson. The bitter lesson, which I think is like a great essay. Recommend everyone to read it if they haven't. Very badly and shortly summarized, I'd say it's just any kind of extra intelligence that you try to imbue into a system by being smart will lose to just more compute. And it's all about, does it scale with data? Can you search? All solutions comes from data and search. So we are progressing on like architectures and like more novel architectures of how to consume all this data with these modalities, etc., etc. But I don't believe that's where the big win is. Like the decent architecture versus the incredibly good architecture when it comes to how you learn on these big models, the difference isn't that big. The difference is the data. Yeah. And it's just, can you create the data that gives you the results that you want? And it's back again to like the diversity of that data and the richness of the data, right? Data that has all of these modalities, including the ability to like see how what you did actually changed the world, is a lot more rich. And how much of this data can you actually generate? And how can you generate data there that is new and novel, that you haven't seen before? So I think like sometime in the future, this is not when we're rolling out now, but like sometime in the future, you will have a lot of robots out there. Whenever they don't have anything to do, they will practice. And they will practice on whatever like robots currently aren't so good at. And it's all about just finding enough data that shows you a different angle on the same problem, that you will learn more about the problem. So it's, to answer your question more concretely, it's the same as most companies who train big models and foundation models. You have a big transformer architecture, you put all of your data in as tokens, you find smart ways to tokenize it, like but the text is pretty simple. It's also pretty well established now how you tokenize images. Video is starting to become pretty common knowledge how you tokenize it well. And same with audio. And it's also, so it's figuring out how do you tokenize like your state, how you tokenize your touch and feel of the world and like the sensory information that comes into that. How do you tokenize that you actually knew which action you were taking that led to this observation, and using that to train better models.
Earlier, you were talking about how the PC sort of becomes this generalized system, and you could do things that you might, are maybe almost too dumb or simple for such a great generalized system like a calculator, but it's still really helpful to just have the calculator there. You've talked a lot about like the humanoid being sort of the ultimate ecosystem for robotics. I'm curious what that ecosystem sort of looks like. Like, does this mean it's open to developers? What does that even mean? Like, what is a robot? App. Like, what does this ecosystem look like in an ideal world?
In an ideal world, it's pretty easy for you to teach a robot how to do something as a consumer, right? And this really opens up an ecosystem where we can share all of these like skills or experiences or whatever that we create, right? So I've had a robot at home for quite a while because, of course, we need to dog fit this. We don't need to test it out, and also it's really fun. And
so you've had an Eve at home, I'm assuming?
Yeah, I have an Eve at home. I'm about to get my Neo. Looking forward to that one.
That's so cool.
It's pretty surprising what I feel like has been some of the most useful use cases. So whenever I'm not at home, as long as I have my headset with me, I can just log on and be at home. So simple things like I'm at the cabin and I can feed the cat. I can receive a package at the door.
How do the cats react to Eve?
The cat doesn't react at all because the cat is used to Eve.
Right? But at first was the cat like, what the hell is that? Or not really?
Not really.
Really?
It's very quiet. Huh. Right? That's another thing that people don't really realize is how much noise most robots make.
I just asked this because cats freak out when a plant falls over and they act like they're dying, but that's really cool. So
that actually didn't react that much.
Has the cat ever showed affection to the robot? Like it purrs and like
No, not really. The kids though.
Kids like it.
Yeah, the kids love the robot. And like for Eve, which is the previous version, which is a bit bigger and heavier. Sure. So that's been more like keep the kids away from the robot, which isn't so easy because they love the robot. But no, it's been quite a journey.
Obviously, a huge part about having this in the home is the ability to afford it. And I think traditionally people are like, yeah, there's no way that an advanced humanoid robot will cost anything less than like a Ferrari or something. In this case, your robot doesn't cost that, and it will get cheaper over time. I'm curious how the hell you've made that possible, and yeah, if you could walk me through sort of that journey of cost and.
Yeah, it's a deep rabbit hole. So, I mean, first of all, like any product that you want to design, you can't really retrofit in cost. It starts day one. It's like, okay, I'm going to create this. How do I create it so that it's as manufacturable as possible? And it has to guide the technical direction that you choose. And there's a lot of like pretty simple first principles thinking here. It's just very hard to do in the real world when you like face problems and you have to like just keep your grade and just keep grinding at it. But from day one, just like make sure, okay, how much materials do I need? Like if I make a very lightweight, efficient robot, if it weighs half of what my competitors' robots weigh, I mean, I'm going to spend half the money on materials. If I can really, really, really get my motors light and my actuation system light, I can save so much money because copper and neodyne magnets, that's the most expensive thing you have in there.
Why is that?
It's just some of the rare metals on Earth. And they cost a lot of money. So like you want to reduce how much you have to use. How do you design a system so that, for example, manufacturing tolerances don't have to be very strict? You want to make sure that like if your system is pretty inaccurate, you still just like calibrate and things go fine. Yeah. And the way we do this tendon-based system, for example, has these beautiful properties where it doesn't need to be very accurate at all. If you have this super precise harmonic drive gears, for example, this is one example, there's many systems like this. You need like a very special type of alloy to kind of be able to package this much gearing into such a small package. It needs to be incredibly accurately machined. And it's just like, it's a very expensive device. And you can't really do that if you're going to do this in an affordable manner. So then you need to take a step back and find out like, okay, can I solve this some different way? And I think it's really, really important that you control your own destiny. You have to really go fully vertically integrated. You have to control your supply chain, your manufacturing. You have to build the machines, build your machine. And one thing about that is that you can save a lot of cost by just getting it done right. But actually the most important part is that you can connect your engineering to your manufacturing in a proper manner. So that whenever something is hard to do, the people who have to do it can go up and tell the designer, like, what the hell have you done here? Like, this doesn't work. Or like your supply chain guy can say, like, do you realize how expensive this kind of material is? Like, we should figure out a different solution. And creating that collaboration across those disciplines, which you lose if you outsource your manufacturing.
You've been spinning up a manufacturing factory in Norway for a while. Like I've seen it. I've seen footage of it. And going from, you take raw materials in and robots come out, and you don't have a huge space. Like it's pretty impressive, and you're about to make way more. Can you sort of share how many more you'll make, and the rough timeline, very roughly, and like, but even like just the ballpark, and like how is that possible? How does that work?
Yeah, well, we can do ballpark at least. So we've had like an internal mantra for quite a while, which is scale by 10 every year. So we did like 10 EVEs, then we did close to 100, and then we're going to do thousands of Neos, tens of thousands of Neos. So this means thousands of Neos in 2025, tens of thousands in 2026, hundreds of thousands in 2027, millions in 2028, and you can do the math.
That's hard.
So far we've been on target, but it's really hard. It's been really painful. I mean, it's not like we're there yet, but it's also like not like we haven't done some of this before. So for Eve, for example, we peaked between 10 and 20 units per month on the previous line. And for Neo, we're going to basically 10x that, right? And it's a lot of organizational pain, right? You need to build out how it is to execute as a manufacturing company, which one thing is all the systems that needs to just be in place for you to be organized and efficient at a scale with respect to like supply chain and materials and processes and traceability and all these things. But it is step by step.
Yeah.
I think a mistake people often do is think that like they can go manufacturing from like 1 to 1 million, and like clearly you can't, right? You have to walk the steps, and you can walk them pretty fast, but you still have to walk the steps. Sure. So we're taking, I'd say, a bit of a humble approach to this. I think demand far outstrips supply, but you still have to walk the steps. So feel very confident right now, since we're building pretty large batches of Neo now already on a new factory line, that we will hit our targets for next year. Very confident about 2026. Something kind of magical happens when you go from like tens of thousands to hundreds of thousands and millions. And it's traditionally like you see a lot of companies fail. It's very painful. And you need to make sure that you have the best people. And people who have done this before. And that you really leverage that you have the full understanding of your product all through your organization, right? And that if anything goes wrong, you can redesign, you can fix it. And that's, again, kind of like back to controlling your own destiny by being vertically integrated and controlling your own supply chain. You actually have you can't blame anyone else. You have the power to fix this if something's wrong.
I feel like
it'll be a lot of work.
Yeah.
Yeah.
Well, I'm excited to follow up as you guys take that journey, that 10x journey every year. I feel like bigger companies, as small companies become big, they struggle to maintain that same amount of communication and quality of hiring that they did in the early days. How do you sort of plan on doing that? And do you have any sort of mental models for how you handle and ask your team to handle company communication?
So first of all, I 100% agree. Like as you scale, there's no way you're going to keep the same efficiency. So first of all, just realize that and own up to it, right? So hardcore R&D does not scale. So keep your team as small as possible. I think about like almost like, you can think about it like a football analogy here. You get 11 players on the field. After that, it's just chaos. So 11 players. So make sure they're the best freaking 11 players in the world. And then make sure you build everything around them. So all they need to do is play football. Right? So it's like organizationally, for example, HR is not there to make you do your hours and make you do this, make you do that. They're here to help you so you don't have to do any of these things. They're here to maximize your impact by letting you do your job. And then, like you say, communication doesn't really work that well. In general, it's very hard. And the way around that is to give people a lot of agency. You need really smart people who they're mission oriented. We're all in the same boat. There's no ego. There's no politics. We're building humanoid robots. We're shipping them to the home. We're solving the problem. We're going to have a huge impact on humanity. And we all care about this, and that's all we care about. And that mission always comes first. And we're very lucky in that we have a very clear view of what we're making. A lot of companies are like exploring what to do. We're very mission oriented and very lucky in that sense that we can just hone in on that and get it done. And then this needs to be reflected in your company org structure. Like you want to really keep a minimal amount of layers, keep it super flat, and then just realize that will be chaotic. So I like to view process as a necessary evil. If you don't have process, nothing gets done. But you don't want more process than absolutely minimally needed to get to peak efficiency. You'd rather have 50% of what gets done in your organization be useful, and everyone's firing at like full cylinders, than have 90% of what your organization do actually be useful, but everyone's like hamstringed from doing anything useful. So you have to really be disciplined about like not letting fear drive your decisions, because if you want to feel fully in control of everything that's going on, you're going to slow things down. And like you said, as you scale, communication. You do need a bit of different people. Like the profile kind of changes of like who excels in your company as you grow, because communication becomes important. But I do think keep it as small as possible and don't get tricked into like following all of the classical business advice of like process. You need layers, you need reporting. Like those things are to some extent needed, but they're not there for their own sake. They're only there if absolutely strictly needed to get something done or to comply with some regulation. They're mainly in the way. Yeah. And this is where it gets really hard because manufacturing is very different. Yeah. So that's how you run your R&D. Now your manufacturing is more like military discipline. Everything needs to be the same. Everyone needs to know exactly what to do. And combining these two into the same organization, I think that's actually the biggest challenge. And that's where most companies fail. If you think about like, it's a very short list. I think like, at least in the West, I think I can only come up with one example, which is Tesla, that has done this pretty well. They've managed to scale their organization on the manufacturing side to be huge, very efficient. But they still kind of kept the kind of lean, agile mentality as a company.
They keep these separate R&D offices, though, where it's like, the small couple 100-person teams, and then the manufacturing org is huge across the country.
But they do also have a lot of co-location of manufacturing and engineering in the beginning, right? So like if you think about like a project where, think about like their new car they're designing, for example. So it's designed typically by engineers sitting in the same area and facility as the manufacturing plant is getting built for like the smaller first line. Now, once you scale it, it's different, right? So like, let's just clone this all over the world.
Right, I'm just saying it's still small, but you're right. It's not like the same size as like you guys right now or a 30-person team. That's true.
Yeah. So like we're 150 people now. Yeah. So we're starting to run into all of these problems. Yeah. And I think you said hiring. That's incredibly important. Until a few weeks ago, I interviewed everyone we hired. But at some point, it's like, I'm slowing this down too much. It doesn't work. Yeah. But I think that's been incredibly important. Because as an organization, we needed to learn how to hire. And we needed to learn who to hire and like what to hire for, etc. And just being that ultimate filter and creating that feedback loop to the hiring managers in your team of like, this candidate wasn't good enough because of this. This candidate was great. And through that, like hiring sets your culture, basically.
Yeah. This next question is a little weird, but I like asking founders this because I think it's cool. Can you try to describe how you think your brain works?
Man, if I knew that, I would already have solved the robotics thing. So if you think about like from like a classical point of view, I say like I'm a very visual thinker.
He's a VLM.
I'm a starter, not a finisher. To a fault, to the extreme. It's like, yeah, you can ask my wife. I never finish anything. But I can start almost anything. Doesn't matter how complex it is and how like long of a horizon you have to think, and it's like, I can be stupid enough to start. And I can stay there, but when it's 95% finished, I'm kind of like, oh, it's done.
Well, so seemingly though, the organization, knock on wood, today it seems like it's good at finishing things.
Oh, clearly, because I know this.
So then you hire for it and you build a team around it. Got it. Cool.
Yeah. And I try to discipline myself, right? So we're about to launch Neo, and I'm like, fuck yeah, Neo 2 is so good. And I'm like, no, I can't go design on that now. We got to finish this. So but that's like my intuition. I'm jumping to the next thing. Right?
How do you fight the fight between like, oh, I need to change as a person to be better for my company versus I should just hire for who I am?
I hire for that.
Okay, so you have no guilt with that. You're just like, it is what it is. I got to do it.
I do think yes, you need to develop yourself as a founder as you grow. But I don't think I can change who I am. I think the thing I've learned the most about, as I kind of like feel like I've grown as a person through scaling the company, is people. Like how to manage people and how to be empathic and kind while still kind of being fair and strict. And that's not something that really comes natural to most people like me. I'm an engineer, right? It's not my strongest suit. But if you want to build a great company and you want to really have people being super efficient and successful, you have to manage people really well. And I think that part of it is taxing in the long term, but incredibly important. It's back to the culture, and we're one big family, and families sometimes fight, and need to make sure we have good rules to play by, and everyone gets along.
When did you decide that? I mean, you guys have these like sort of 3 corporate values pinned up in one of your meeting rooms, and one of them is be nice, and even here you're talking about it, and I'm curious when you decided on that value and why you decided on it. And like for people watching, like wondering why I'm asking this question, it's like a lot of people who build really intense things, I think probably do not hold that value, and they're just like, do whatever you got to do to get it done because it's so hard. On the one hand, I can really like understand that. On the other hand, I was like, man, that kind of sucks. Like, why can't you do both? And I'm curious like how your mental calculus on that balance happened and how you landed where you landed.
Yeah, so I mean, the culture got built because it's what I believe in, and as a collective, what we believe. And they're like, we expect people to work really freaking hard, right? You don't win the Olympics without working really hard. And we expect people to be very smart. Like if you come work here, it's because you're among the best. And if that is going to be something that you do, like you're going to spend all of your time here, going to work your ass off, and you're one of the best people in the world, then you better be nice. Because if not, it's not going to work, right? If you're going to spend that much time somewhere, there has to be some fun in it. It's more productive, right? So that's kind of like the summary of why I think the culture is right. Now, how did we actually phrase it like this? How we come up with the specific values? That's way more fun and way simpler. And I think we have some of the most honest, true core values of any company, because they were actually from a very late night on a party from one of our early employees who said like, this is who we are. And it was those 3 core values. It's like, we're smart, we work really freaking hard, and we're nice. And it just rang so true. So it's like, yeah, fuck, everyone just agreed until it's like, that's who we are.
So I imagine sitting around and be like, we're not nice.
So it wasn't like, there wasn't some corporate bullshit where like someone sitting with a consultant in a room and coming up with like, what's our values? Which doesn't make sense, right? That's not what values are. And that we kind of decide like, this is the culture we want to keep because I think it's the most efficient company. It's the most efficient culture.
Well, I applaud you for it. I think like a lot of people in building hard stuff like don't feel that way or don't think that it's okay to feel that way. And so I think that's wonderful. What's something you know or believe that you think other people don't or very few other people do?
Why our body works the way it does. Like, it's like this infinitely deep rabbit hole of reasons for like every minute detail, like how your body works.
Do you think we fully understand it? Like,
No, not at all.
Yeah.
I'm just saying like,
right.
I feel I have a pretty good understanding of that, better than most, and how this kind of connects to everything from like how you interact with the world to how that affects how we learn. From like a first principles physics point of view, right? How do you think about biomechanics from a physics point of view?
No, it's good. I mean, if you could talk more about it, or even in the context of like, I know a lot of roboticists that would sort of laugh, when they hear about people doing tendon drives nowadays or doing muscle like robotics, and it's no longer in vogue. Like I think that was very popular in like probably the 80s, 90s maybe, and now I think a lot of roboticists today are like, oh no, that's not a industrial robots don't use it, therefore it's done. And I'm curious like. You don't seem to ascribe to any of the hyper what's in vogue or not in vogue. You're just like, we're finding the best system from first principles and building it. And I'm curious what some of that thinking looks like, specifically around like how you know and understand the human body works in the context of robotics.
It's like, I think this is one of the things that makes a lot of founders and companies fail, is over time they got convinced that they're wrong. If you spend all your life thinking about this problem and studying it, and you have like some intuition, but like this is the right thing, and then you start doing it, and everyone will tell you like, we've been smoking, right? This isn't going to work, or people have tried this before. Didn't you see? Like, why are you doing this? Yeah. And then you try anyway, and then a couple of years go by. And it starts to seep in that everyone every day is telling you like, you're obviously wrong. And people give up. Don't give up. Like all major innovation comes through like super hard conviction and grit, right? It took us 6 years to get from like, think this will work to this is actually reliably working. For example, when it comes to tendon drives. There's a lot of like problems that people say like they're not solvable, like durability, reliability, robustness, manufacturability, all these things. But they're solvable. But they're not solvable in like a 3-month time frame. And I can go through like a long list of companies, even in robotics, that they had the right intuition. And then they changed direction. And they made something kind of bland that was like everyone else's opinion, didn't really work better than anyone else's, and they died. If you just stuck to that intuition, if you dedicate your life to a problem, your intuition is probably pretty good. And I'd rather be wrong and like just really fail than to just water out. So like, if you have conviction about something and start a company based on it, stick to it until you're dead.
I love that. It's interesting that like we've seen so many innovators and scientists prove that true. Like you think of Edison, you can think of Musk, you can think of like so many examples, yet we still have such a hard time remembering that and internalizing it, which I find super interesting.
But it's really painful, right?
Yeah.
Like people telling you every day that like, come on, like.
No, I'm going through this right now with what I'm founding. Like,
Yep.
I 2 weeks ago, I had like an employee who was like, this just isn't realistic. Like we should like scale it back. I was like, yeah, you're right. Because it made sense. And then a week later I was like, no, they're totally wrong. I don't care if it's crazy. Like, we can actually do it. And so I can relate to that. What's something you wish kind of more people asked you about when you're talking about 1X?
How do you think 2040 will look? Everyone's interested in asking, like, oh, what's happening in the next 2 years, 3 years, 5 years, right?
Yeah.
And then we can get into all of the debate about, like, will we like meet a brick wall in AI? Yeah. Will the manufacturing scale? How will this look? But let's just say, like, what about 2040? How will that look? Because now we can like kind of like say, okay, oh, we could probably figure out a lot by 2040. We always underestimate technology in the long run, right? So then you can get into like, first of all, I'm so fucking like glad to be alive. I am so lucky. I'm born into this tiny window in time in humanity.
It's insane.
Where we get to be part of basically, hopefully creating artificial life. Yeah. And I get to contribute to this.
Well, and beyond that, like, we're also alive at the time we're going to space, that we have computers to boot, that we're building, like, not even just AI. Like, it's an insanely good time to be alive.
It is, right? There's like, we're going to figure out, and all this is going to come together, and like, we're going to figure out to a large extent, if it is possible to figure out, how the universe works.
Yeah.
Right? And I think in 2040, humanity will just look completely different. Like, we will have solved energy to the extent that we can harvest almost as much energy as we would like for our current kind of like projected civilizational needs. Like at some point you get into like type 2, type 3 type societies and other things. But like, let's skip that one for now. I don't think that's 2040. And then we just say, like, okay, we've mastered energy. We've mastered the conversion of energy into mechanical work. We have an infinite supply of products and services. We can do everything in a completely sustainable manner. Like, there's absolutely no reasons to cut cost because you have infinite labor. And everyone can have everything they want of material goods. This is going to be like way bigger impact than the agricultural revolution. And it's freaking amazing to get to be part of that. And I think it can create a beautiful world. And I think there's so much dystopian sci-fi here, and it all gets lost in that. I don't think that's how it's going to go at all. And I think building a future where we can like care about what makes us human is going to be a lot of fun.
Yeah, the dystopian sci-fi thing really annoys me. How much of our stories are like that? What is your favorite sci-fi story?
It's a dystopian one, but yeah, since you ask. I mean, nothing beats Do Androids Dream of Electric Sheep, like the Philip K. Dick novel behind Blade Runner.
Why?
It's just got a special place in my heart. I grew up with it, right? I read it. I don't know. I watched Blade Runner probably 500 times while growing up, and really inspired me to do what I do. It's just incredible to think that like this was written in the 60s. It's so visionary, and yeah, it's an incredible story because it really connects like the humanity of all of it into this story of how we integrate androids into our society. And I'm excited to get to be part of exploring that and do a better job than they did in Blade Runner, but I think we can do a better job.
Should we get more people to care about building the future and excited about it?
And clearly. I mean...
yeah, I feel a little stupid asking that.
It's like, well, we can go deeper on why, but okay, should we get more people to care? I think we should get more people to care about everything. Like, it's the root of everything that is good is just people caring. If people care, things generally go really well. And I think you're like setting me off on a tangent here, but I think it's one of the biggest problems in our society today is people have a lack of purpose. Right? How do you get happy without purpose? If everything's about like, how can I do less? and have more, you're not going to have a happy life. You need to have purpose. And I think that kind of requires a gradual shift in culture for like, how can what I do actually impact the world positively so that I feel every day when I do something, I have a good reason to do so. And it feels good because it has purpose. And we used to have that. And I think we need to go back and like find.
Why do you think we lost it?
It's a really good question. I think, I don't think we fully lost it, but I think we watered it out. And I think purpose is very easy if things are very hard, right? So if you're in a situation where like, okay, I need to really focus on surviving, you have a lot of purpose. Like I need to focus on having my family and friends survive, you have a lot of purpose. And I'm not saying we want to go back there. We want to have as pleasant a life as possible. But somewhere along the way, we might have taken like one step too much into individualism and like the worship of like the self and the individual. And a lot of our purpose comes from the community. And if you only think about yourself, then it's very hard to find happiness. It's very hard to find purpose. Like you can find momentary pleasure, but you can't really find happiness and purpose because that comes through making things better for like your wife, your kids, your friends, society, the country, the world. Like there are many different levels here, and none of them are like right or wrong. But I do think ensuring that whatever the impact of your life is a positive one will give you a lot of happiness. And yeah, we should strive a bit more to ensure that our actions have purpose.
My last question for you is another one I really like asking founders. And it's, what is your current life philosophy?
I haven't really defined that. That's a deep question. It's like the cliche, like do whatever feels right. But I mean, no, it's not like just then and there for like reward, but I care very little about social norms. Like I love to work on humanoid robots. I have a wife and 2 kids. I have my friend living with me and my wife and my 2 kids. And I have another friend and she's like periodically living with us and like we're building a new house where we have a lot of friends plus us, even though our family is gonna live together because it's just way more fun. And just like, don't let anyone else tell you what you want to do. Like do whatever as long as you're not hurting anyone, like do what you think is giving you the best quality of life. And things will just be a lot more fun.
That checks out. Well, Bernt, thanks for taking the time to do this, flying out here to do it, and thanks for building 1X. I'm excited to have one in my home.
Oh, thanks for hosting, and I really look forward to this.
That's awesome.